Okay, so I'm going to do some more problems here involving Newton's second law. All right, so here we go. So here's a little model rocket. And let's say this has a mass of 1 kilogram. And I know the engine here, by spewing out that hot gas, the gas pushes up on the rocket, and that gives it a thrust force. So let's say that that thrust force is 20 newtons. And then the question is, what is the acceleration of the rocket going to be? So first I'm going to draw the rest of the forces acting on the rocket. So this is when it lifts off, so it's not on the ground anymore, but it still has weight, and the weight of anything near the surface of the Earth is mg. So there's your picture. I'm going to use up as positive direction, and I'm going to write Newton's second law, which is net force is equal to mass times acceleration. So the net force on this is going to be the thrust force minus the weight of the rocket is equal to the mass of the rocket times its acceleration. And now I can put in some numbers. So the thrust force is 20 newtons. That's this number. Minus the weight of the rocket is its mass times gravity. So 1 kilogram. And the value of little g is about 10 meters per second squared. 1 times 10 is 10, and it's newtons. So 20 newtons minus 10 newtons is equal to the mass of this rocket, which is 1 kg times A. So 20 minus 10 is 10. So 10 newtons is equal to 1 kilogram times the acceleration. So yeah, basically divide both sides by 1 kilogram. And a newton per kilogram is a meter per second squared, believe it or not. Yeah, so the acceleration is about 10 meters per second squared. All right. Now, part 2 of this problem. You didn't know there was going to be a part 1. I mean part 2, did you? Here's part 1. Yikes. Yeah, there's a part 2. Roman numeral 2. So part 2 is going to be this. If the engine burns for 3 seconds, right? Because these little engines, when you ignite them, they have a limited amount of fuel. So that engine will burn for a few seconds, then it'll burn out, and it will no longer exert a thrust force. And typically these little model rocket engines will burn for a few seconds. So let's say the engine burns for 3 seconds. Then we want to know a couple of things. So how fast is the rocket moving? What is the rocket's velocity? So how fast is the rocket moving when that engine burns out? So, acceleration, velocity. Oh yeah, I know. About V final is equal to V naught plus AT. Okay, we've spent about 3 months looking at this whole kinematic equation. The initial speed of the rocket is 0. It starts off at rest. So that's 0. So this is pretty straightforward. The final velocity is going to be the acceleration of the rocket, which we just figured out is 10 meters per second squared, times, and the engine burns for 3 seconds. So 10 times 3 is 30. And the seconds here cancels with one of these guys. So I've got 30 meters per second. So that's how fast that thing is going after 3 seconds when the engine burns out. Next part. How high is the rocket? Oh, yikes. How high does that rocket go? What distance above the ground is that rocket? So, oh, wait, there's an equation for that. Let me draw a little picture here, though. So here's the ground. And this is not drawn to scale. And so that rocket is initially on the ground. And then that engine burns up and burns. And at some point, the engine burns out. Okay, and so then we want to know, so yeah, what is that distance? We can call it delta x if you want to. We call it delta y. So during this entire phase, it has an upward acceleration of about 10 meters per second squared. And we want to know the position, so guess what we can do? How about delta x is equal to v naught times t plus 1/2 at squared. And so again, this is an equation we've used for several months now, so that should be vaguely familiar. All right, so this term is 0, so this first term goes away. So then its height above the ground is just 1/2. The acceleration we figured out was 10 meters per second squared, and the engine burns for 3 seconds. So now, also just to avoid confusion, that 10 meters per second squared, that's not little g. That's not the acceleration of gravity. I mean, I know it has the same value. This is the acceleration of the rocket because of how much force that engine is exerting. So delta x, so let's see, so 1/2 of 10 is 5. And then 3 squared is 9. And 5 times 9 is 45. And the units end up being meters. So then when that engine burns out, does that rocket just all of a sudden stop moving up? No, it doesn't stop moving up because it's moving 30 meters per second. It's going to keep gliding up and slow down, and at some point up here, it's going to finally stop. So now, oh boy, what is this distance? How high does it go? What is the total height it ends up above the ground? Because it's going to keep gliding upward, right? So let's call this second, I know this picture is getting crowded. Let me redo the picture right here. Yeah, this problem has multiple parts to it. So the rocket blasts off. And then at some point the engine burns out. And we've already established that distance is 45 meters. But then it's going to continue to cruise upward and slow down and finally stop moving up. So we could say here that this V final is 0 meters per second. And so, yeah, what is this additional distance? Let's call that, how about to avoid confusion, delta y. Because we already used delta x down here and we got 45 meters. So for this next part of the motion, you just treat this as a separate problem if you wanted to. Let's see, so what is the velocity of the rocket right here when the engine burns out? Oh, that was 30 meters per second. Also, when the engine burns out, the only force acting on the rocket now is gravity. And that means that the rocket now has an acceleration of minus 10 meters per second squared. This is the acceleration due to gravity. It's negative because in our coordinate system, up is positive, and it's slowing down. And so, oh my goodness gracious, do we have an equation for this? Yeah, we do actually. Probably have a couple of different ways of figuring this thing out. You know what? First of all, I'm going to figure out the time, right? So how long to stop moving up? All right. So I know that this portion of the flight took 6 seconds. I'm sorry, 3 seconds. Because that engine burns for 3 seconds. Now the question is, what is this time up here going to be? I know the problem's getting a little crazy here because you've got a lot of different terms. Well, let's see. It's moving 30 meters per second when the engine burns out. It's losing 10 meters per second every second it's moving up. So how many seconds to stop? It's going to take 3 seconds to stop. Or if you like, we could do this, using these equations. How about this one? V final is equal to V naught plus AT. So, and remember, we're looking at this portion of the problem up here after the engine burns out. So the velocity way up here is 0. And the initial speed of the rocket when the engine burns out is 30 meters per second. And the acceleration is minus 10 times t. So to solve this equation for t, move the 10t to the left side. So 10t is 30 meters per second. To get the t by itself, divide both sides by 10. All right. And so 10 over 10 is 1, so we get that t is 30 divided by 10 is 3 seconds, so another 3 seconds. So it takes 3 seconds to get to this position, then when the engine burns out, another 3 seconds to stop moving up. So now, finally, I know this is crazy. So now, how much further does it move while the engine is, after the engine is burned out? So delta y, the easiest way to figure this out would be that just use delta y is v average times t. So delta y. So what is the average velocity? Remember average velocity? Let's draw another picture right here. So it goes up, the engine burns out, and then it stops. So here, it's moving 30 meters per second, and up here, it's moving 0 meters per second. So what's the average of 0 and 30? It's 15. So the average is 15 meters per second, and it's for 3 seconds. This is strange. So now delta y, the additional distance it moves after the engine burns out, is 45 meters. So the total distance above the ground ends up being 90 meters. All right, so we will stop that problem now, and I'll upload this for y'all to look at.